This is the third video of the Quantum Fourier Transform series. In this video, we will build the circuit for Quantum Fourier Transform following a step-by-step approach. The Quantum Fourier Transform is a cornerstone of many quantum algorithms, including Shor's algorithm for factoring large numbers and solving discrete logarithms. First, we will review some key notations to establish our foundation. Next, we will construct the quantum circuit for an n-Qubit register. Then, we will demonstrate that the circuit functions correctly and produces the desired output. Finally, we will create a 3-qubit Quantum Fourier Transform circuit to demonstrate what we have learned. Let's begin with some notations. The first notation we will need is to how to express a variable in binary form. Take a variable j, which we can write as j1, j2, and so on up to jn. In binary form, this translates to j1 times 2 raised to the power of n minus 1 plus j2 times 2 raised to the power n minus 2, continuing in this manner until jn, which is multiplied by 2 raised to the power of 0. The next notation is for representing fractional binary values. We denote a fractional binary as 0.jl, jl plus 1, and so on up to jm. This can be expanded as jl divided by 2 raised to the power of 1 plus jl plus 1 divided by 2 raised to the power of 2, and so on until jm divided by 2 raised to the power of m minus l plus 1. Now, let's discuss an essential quantum gate which is used in the Quantum Fourier Transform, known as the RK gate. The gate is represented by a matrix with elements 1, 0, 0, Euler number raised to the power 2 pi I divided by 2 raised to the power of k. The RK gate is a quantum phase gate. When we apply RK gate to the state ket 0, the output remains ket 0. However, when we apply RK gate to the state ket 1, a phase factor of Euler number raised to the power 2 pi I divided by 2 raised to the power of k is introduced to the ket 1 state. To create the Quantum Fourier Transform circuit, we will use what is known as the product representation of the Quantum Fourier Transform. If you are interested in detailed breakdown of how to drive this product representation, stay tuned for my next video, where I will talk through the process in depth. Let's now express the Quantum Fourier Transform in product form. Suppose our input state is a quantum state of ket j. When we apply the Quantum Fourier Transform to this state, the result can be represented in product form as follows. The state is represented by 1 over square root of 2 to the power of n multiplied by the product of several terms. Each term has the form ket 0 plus Euler number raised to the power of 2 pi I times a fractional binary value times ket1. The fractional binary value is written as 0.jn in the first term, 0.jn-1, jn in the second term, and so on until the last term where we have 0.j1, j2 up to jn. With these notation established, we are now ready to design the quantum Fourier transform circuit for an n-qubit register. The input to the circuit is the state ket_j, represented as ket_j1 through ket_jn. Each qubit corresponds to a line in the circuit, and we will essentially apply gates to each line. On the line corresponding to ket_j1, we apply the Hadamard gate, which creates a superposition. Then we apply R2 gate, using the second qubit J2 as the control bit. Next, we apply R3 gate with the third qubit J3 as the control bit, and so on. This process continues until we apply Rn-1 gate using the second to last qubit Jn-1 as the control bit, followed by Rn gate with the last qubit Jn as the control bit. Similarly, for the line corresponding to ket_j2, we begin by applying the Hadamard gate to create a superposition. We then apply Rk gate sequentially using each of the line below as control bits. For the line corresponding to ket_jn-1, we start by applying Hadamard gate. Following this, we apply R2 gate using the last qubit Jn as the control bit. Finally, for the line corresponding to the bottommost qubit ket_jn, we only apply the Hadamard gate. Since there is no line below ket_jn, there are no control bits available for further ket_j gates. The output of the line corresponding to ket_j1 will be a superposition of two states, one ket0, another where the state is ket1 but with a phase factor applied. The phase factor is given by Euler number raised to the power of 2 pi times fractional binary value formed by digits j1, j2 and continuing up to jn. For the line corresponding to j2, the output will be similar, but the fractional binary value starts from j2 and ends at jn. This means that the phase factor for the ket1 state is determined by the fractional value formed by the digits of the second qubit and all subsequent qubits. Each line follows this pattern, with the fractional binary value starting from the current qubit and including all qubits below it. For example, second to last line correspond to ket_jn-1 will have a fractional binary value of 0.jn-1 followed by jn. The final line correspond to ket_jn will have the simplest fractional binary value of 0.jn as there are no qubits below it. Let's write out the complete output of the circuit so we can compare it with the Fourier transform in the product form. When we write the output of this quantum circuit and compare it with the product form, we notice that the two match perfectly except for one key difference. The qubits are in reverse order. To correct this and ensure the output align with the expected sequence, swap gates are included at the end of the circuit. These swap gates reverse the qubit order, aligning the output with the original input sequence and confirming the correctness of the quantum Fourier transform. Now let's verify the correctness of this quantum circuit by carefully analyzing the output of the first line corresponding to ket J1. We will do this step by step by applying all the gates sequentially. Starting with the input state ket J1, we first apply the Hadamard gate. The result is a superposition state which can be expressed as 1 over square root of 2 multiplied by ket 0 plus Euler number raised to the power of 2 pi I times J1 divided by 2. You might be wondering how this result is derived. Let's break it down. First, consider the case where J1 equals to 0. Substituting 0 in place of J1 in the exponential eliminates the phase factor because any power with 0 exponent equals 1. Thus the result simplifies to 1 over the square root of 2 multiplied by ket 0 plus ket 1. This is the expected result when a Hadamard gate is applied to ket 0. Next, consider the case where J1 equals 1. In this case, the phase factor becomes Euler number raised to the power of pi times I. From the unit circle, we know that Euler number raised to the power pi times I is equals to -1. Therefore, the result becomes 1 over square root of 2 multiplied by ket 0 minus ket 1, which matches the expected output when a Hadamard gate is applied to ket 1. On this intermediate result, we apply the R2 gate. Recall that RK gate is a phase gate that does not affect ket 0 but introduces a phase factor to ket 1. Specifically, the phase factor is Euler number raised to the power of 2 pi I divided by 2 to the power of k. For R2 gate, k equals 2. Since the R2 gate is controlled by J2, the phase is applied only if J2 is equals to 1. To incorporate this condition, J2 is included in the exponent of the phase factor. We continue this process applying RK gates sequentially, with each controlled by corresponding qubit Jk. The final gate in this sequence is Rn, controlled by Jn. As we add the phase factor introduced by each gate, the cumulative result becomes 1 over square root of 2 multiplied by ket 0 plus Euler number raised to the power of 2 pi I times the sum of J1 divided by 2, J2 divided by 4, so on up to Jn divided by 2 to the power of n. Using our fractional notation, this can be expressed as 0.J1, J2 up to Jn. This is precisely the intended output for the line corresponding to ket J1. The same logic applies to all other lines in the circuit. Each line contributes a superposition state with a phase factor determined by its respective fractional binary values. By following this reason, we verify that the circuit produces the correct output for all lines, confirming the correctness of quantum Fourier transform circuit. Let's apply what we have learned so far to construct a quantum Fourier transform circuit for 3 qubits. In this case, we have 3 lines corresponding to qubits ket J1, ket J2 and ket J3. On the first line, we begin by applying Hadamard gate, followed by R2 gates with J2 as the control bit, and then R3 gate with J3 as the control bit. On the second line corresponding to ket J2, we apply the Hadamard gate and then R2 gate with J3 as the control bit. Finally, on the third line corresponding to ket J3, we only apply the Hadamard gate. To ensure that the qubits are in correct order in the final output, we apply a swap gate to exchange the output of first and the last line. If the circuit had more qubits, additional swap gates would be required. It is worth noting that R2 gate is equivalent to S gate and R3 gate is equivalent to T gate. Therefore, instead of implementing custom RK gates, we can use the widely available S and T gates. This concludes this video. If you like this video, please consider supporting this channel. See you in the next video. Bye for now.